Welcome back. Where we left off last time was we had formed our two hypotheses about a population parameter, and we talked about how we made sure our data was valid so we could actually use it in the analysis, and then we computed our sample percentage. And now we want to get to the punchline of hypothesis testing, which is what we call statistical inference. An inference is where we make a generalization about this huge population from our itsy bitsy sample. So this is inference, going from the sample to saying something about the population. And hypothesis testing is one type of statistical inference we can do. So to explain kind of the logic of what we're going to do here, I'm going to go back to this court trial analogy. And let's suppose I am being put on trial for a capital crime, like say maybe murder, right? Capital murder. And at the beginning of the trial, the likelihood that I'm innocent, or not guilty, if you will, given the data against me is 100%. So if the prosecutor comes in and says nothing, there's a 100% chance I'm going to walk out of the court a free man. But of course, that doesn't happen. Prosecutor starts to present evidence. So first, they present evidence that I was arguing with the victim, right? But it's still possible I could be innocent, right? That's not so damning of evidence. But then I'm seen leaving the scene of the crime. That lowers the likelihood I'm innocent. Then they find my fingerprints at the crime scene. And then maybe I had a motive. Maybe the victim was a male and he was, having an affair with my wife, right? Now I have a very strong motive to want to kill this person. And then maybe they find the murder weapon, maybe a gun in my car. And then finally, they find the body in a freezer in my basement, right? I always joke that I had the body of a 20-year-old in my basement. No, I'm joking. Okay, so now what happens though? As all this evidence is presented, right, the likelihood that I could be innocent begins to get smaller and smaller and smaller and smaller until at some point the jury has to change their mind, right? And this is what's going to go on in a hypothesis test. We're going to create some sort of probability scale like this. And unlike a murder trial where that line at which they change their belief is kind of fuzzy, ours is going to be really nice and quantitative. We're going to see how we can make this decision. So we're going to use this example that we've been talking about with the motorcycle injury rates in Florida. And we said that our null hypothesis was that after the law was repealed, the percentage of people in accidents that were injured was 80%. The law was repealed. We collected data afterwards to test to see if there had been a change. And we find out that 425 people were injured out of a random sample of 500 people that have been in accidents. And so we want to use this sample percentage to say something about the population percentage. And how do we do that? So this is the logic behind how we make decisions in statistics using hypothesis tests. So if the null was true, then the percentage of people who were injured in accidents after the law was repealed would be the same as before. No change would have occurred. It would have been 80%. And if we took a whole bunch of random sample of accident victims that were on motorcycles in Florida, the percentage of people who had been injured in those accidents would form a random scatter, about 80%. We know that when we take random samples, the estimates are scattered around the actual parameter value. But we want to make this picture more precise and more quantitative so we can make decisions. So now we're going to introduce the central limit theorem. The central limit theorem actually tells us what this pattern of the scatter looks like. It says that it's a normal distribution. And so it looks like this. And so this is what the population of sample percentages that are taken from a population where the true proportion in the population was 80% look like. Okay. Most of them are going to be around the population parameter value. We're going to get a few samples where there's a really high percentage, like 86, a few samples where there's a really low percentage, like 74, and overall it will look like this. And sometimes we call this distribution the null distribution. This is the distribution of sample percentages that we get if the null was true, if the population percentage was 80% in this case. And so how do we now use this more quantitative picture to make decisions, okay? Well, our question is, has the population percentage changed? Obviously, there's some evidence that it's changed, right? I mean, look, you take random samples, it's very unlikely you're going to get it exactly 80%, so there's some evidence, obviously. But there's two ways to interpret that change. So the first says that the population parameter stays at 80%, and this difference that we're seeing between the observed sample percentage and the population parameter is just due to random variation. In other words, this data value is just part of the random scatter that the sample estimates have around this population parameter. And this would be the interpretation we would believe if we thought the null hypothesis was true. On the other hand, there's another interpretation that says, no, it's too unlikely you could see that percentage, which in this case happens to be 85%, if you take 425 over 500, too unlikely to see that by random chance. And in fact, what's really going on is this data value here at 85% is actually part of the random scatter at a new value of the population parameter. And the question is, how do we tell? Okay. So when we're doing a hypothesis test, this is important, we're testing the null hypothesis. Just like when you're on trial, you're testing the hypothesis that you're not guilty. Same thing here. So what we want to ask is, how likely is it that we got a sample percentage of 85% if it comes from a population where the true population percentage is 80%? How likely is it we could get the sample percentage of 85? And we know that how likely in statistics is code word for percentile. So I'm going to look at sample percentages I would get if the null hypothesis was true and the population parameter is 80%. And now I'm going to compute its percentile. And that tells me how likely is it I got this value in the null distribution. I could use StatCrunch to do that, but we're going to actually see that StatCrunch has a dedicated program just doing hypothesis tests. It's going to do all of this for us. So how do we make our decision? Okay, so to go back to the criminal trial case, right? The idea is that there's some line in the sand, right? There's some point where the jury says, now you've gone beyond a reasonable doubt. Above that, you're not guilty, right? So this is some evidence, but not enough. And then at some point, we get to a tipping point where now the jury changes their mind. The default belief when you came into court was that you're not guilty, but now there's so much evidence, the probability that you could be innocent given all of this evidence is so small, the jury flips and changes their belief about you. Or about me in this case, okay. But if we think about this in the context of our problem, we're going to do the same sort of thing. This is the probability the null hypothesis could be true given all the evidence against it. And the evidence against it is going to be the p-value. It's going to be that percentile we just looked at. And when that percentile is really small, that means it's really unlikely the null could be true, because it's really unlikely we could get a sample percentage from the distribution of sample percentages we'd get if the null was true. Now, unlike jury trials, which are vague, right? Who knows where you draw this line in the sand? And this is exactly the reason why juries deliberate, right? They're trying to kind of shore up their standards of how they're going to convict someone or if they're going to convict them. Okay, this is a kind of airy-fairy and kind of ambiguous here. But in statistics, we set a minimum p-value. It's called the level of significance. Why? Because it's the p-value that is kind of the dividing line. It tells us when something significant happened. And we denote the level of significance by the Greek letter for small a, alpha. Above the significance level, if the p-value is greater than alpha, we're going to say the estimator is not that unlikely to occur. And so we're going to fail to reject the null. We're going to still believe the null. Just like here, we still believe the person is not guilty. If it's below that, then we're like the jury. We flip and we reject the null. Now, how do we do this in StatCrunch? We're going to see two different ways, okay? So if we go to StatCrunch, and I'm going to go to StatCrunch right now, we're going to go ahead and run that hypothesis test for that motorcycle example. So I'm going to start off, I'll take a blank page here, and we're going to go to stats. And now we're going to go to a new menu item called proportion stats for one sample. Notice there's a lot of different options. We're only going to ever use the first two. And so what StatCrunch is asking you is it says, do you actually have a raw data set? The answer is no. So we don't do with data. Instead, we do a summary. We have a summary of the data, right? So I'm going to click with summary. Number of observations is our sample size. And in this problem, we had a sample size of 500. Number of successes. Okay, what is a success? A success means that that individual in the sample was in your category of interest. Well, my categorical variable was whether or not a person in a motorcycle accident had been injured. My category of interest was yes. So I have 425 successes. Notice that success doesn't mean something good. It's not good to be injured in a motorcycle accident, obviously. But it's what I was looking for. So when I find an individual, it's what I'm looking for. I call that a success. Doesn't mean that it's good, okay? Now I'm going to enter my hypothesis test. So I'm going to enter the value under the null hypothesis, which is 80%. And I'm testing that the percentage change, that it's not 80%. And then I click compute. And what I want to do now is I want to examine the output and talk a little bit about that. And again, you can go through and follow along here, or it's always best to work along on the computer, but you have that as kind of a cheat sheet. A lot of the output from the hypothesis test is your input, which is good. You get to check everything. Did I enter the hypotheses correctly? Yes. StatCrunch uses H sub A instead of H sub 1. I mentioned that was an alternative way of expressing the alternative hypothesis, if you pardon the pun, so to speak. And this is my number of successes, sample size, sample proportion. The standard error is another term for the standard deviation of the sampling distribution. So if I went and I computed in StatCrunch this value, if I computed the square root, right, of 0.8 times 0.2 divided by 500, like we've been doing, okay, that would be equal to this value, the standard deviation we've been computing using the central limit theorem. This z-score is the z-score of my sample percentage in this normal distribution, where the mean is 500 and the standard deviation is this. So I claim that this is going to be 0.017. And if I went ahead and I computed the z-score for 0.85, in this normal distribution, I would get about 2.8. And we know that that's not unlikely, that's unlikely to occur. And this p-value is the percentile, okay? And let me show you, I'm going to show you using StatCrunch just so you can kind of see. You don't have to do this, but it helps you get a little bit of a sense of what's going on here, okay? I'm going to split the screen here real quick. Okay, so this is this. And go over to StatCrunch and pull this over. And so what I'm going to do is, not that, try this again. I'm going to go to the normal calculator. Stat calculator normal. And I'm going to enter the mean, which is 0.8. Okay. I'm going to enter the standard deviation, which is 0.01788885. And I'm going to enter I'm going to enter greater than, and I'm going to have to multiply it by 2, okay? So when I'm computing the p-value, I take, and I have a hypothesis test where it's not equal to the parameter. I take the value in the tail and I multiply it by 2. So if I took this value right here, this is half the p-value, and multiplied it by 2 for a two-tailed test, okay, I would get 0.0052. So if I looked at the symmetric tails here, I would get that. And that's what's going on, but you don't have to know that. That's okay. Just to give you an idea of where p-values come from. Okay. P-value is very small, so we're probably going to reject, but we're going to come to that. Now there's another way that you can run a hypothesis test, and that is with an actual data set. And I'm going to look at this Colgate data set that we've been talking about, right? So if I go back up here to StatCrunch and I pull up the Colgate data set and load that up. Okay. It's very similar to what we just did a second ago. So again, I'm going to go to Stat, Proportion Stats, one sample. But now I have a raw data set. I'm going to click with data. And I'm going to have to alter a few little fields here, okay? So the first thing is I have to do is I have to click on the categorical variable, right? Whose percentage I'm testing, which here is whether or not they recommended Colgate. And one of the things you have to tell StatCrunch is you have to say what value for this variable represents a success. What are you looking for? Well, we're looking for the ones that recommended. So the value for the variable for those who recommended was yes. It just happened that the parameter value was 80%. 4 out of 5 dentists, recommend, and we were testing to see if it's less. Okay, so very similar to what we did. And then we're going to hit compute. And so the interpretation of the data of the output is exactly identical, okay? If we go through this, we're testing to see if it's less than 80%. We had 43 out of 50, which is a sample proportion of 86%. Using the central limit theorem, with pi is equal to 80% and n is equal to 50, we could calculate our standard deviation, which is a standard error. I could take my data value and the mean and standard deviation of that normal distribution and compute its z-statistic. And then I could compute its p-value. Now there's an interesting thing about this p-value. Once you get a little familiar with p-values, one of the things you'll notice that this p-value is very, very large. Okay. And we're going to talk about why it's so large. Okay, usually p-values are actually quite small. Okay, but now we know how to run a hypothesis test. We haven't talked about how to make decisions yet. We're going to get to that, but at least now we know how to run a hypothesis test in StatCrunch. And now we want to figure out what to do with the output. So the first thing we want to understand is what is a p-value? P-values are actually very controversial. They're being reconsidered by the statistical community for reasons I won't get into, but they're still very handy and they're used in research on a regular basis. So the p-value, again, is the probability that I could get a sample percentage as extreme as the one we observed or more extreme if the null is true. And again, let's bring up that picture of the random scatter and morph it into the normal distribution to see how we can make sense of this. So this is that random scatter that we would expect to get. And this is our sample percentage, 85%. And the p-value is the percentage of sample proportions above 85% we'd see if the true population proportion was 80%. So it's the percentage of sample percentages above 85% we'd see if the true population proportion was 80%. If we think about what this looks like with the exact distribution, right? So here's 85%. The p-value is the probability in the tail. Okay? We see it's very small. So how do we make decisions with this, okay? Let's put this all together. So large values are values in favor of the null hypothesis. Remember that court trial, right? It wasn't too, I still was very likely I was innocent given the evidence, right? So if we got a value down here, for example, okay, or up here, for example, right, we could see that its p-value, the probability that I could get a value that large or larger, in other words, the percentile for that observed sample percentage is pretty large. So it isn't that unlikely. This isn't strong evidence against the null. But on the other hand, small p-values means it's unlikely that my sample estimate could come from the population of sample estimates I would get if the null was true. So now if I'm up here, it's less likely I could get this value by random chance. It doesn't look like part of the random scatter anymore. And the p-value, again, is the percentile of my estimate, and we can see it's small. It's very unlikely I could get values way out here if the null hypothesis was true. Now, we're going to put this logic together with this level of significance we talked about, right? So here's the thing. How small is too small? Where is that line in the sand? Where do we go from not guilty to guilty? Where do we go from null to reject the null? That's the level of significance. So this tells us when the p-value is too low to still believe the null. So it says a sample proportion is too unlikely to come from a population of sample percentages that were drawn from a population whose population percentage was that in the null hypothesis. We use this Greek symbol alpha, which is the Greek letter for lowercase a, and we usually use values of 1%, 5%, or 10%. The default when no value is given in the problem is 5%, but usually it'll be given in the problem. If it isn't, assume 5%. So sometimes people say, and this is said in the book, that we don't choose weird values like 0.028 because it would appear that we're jury rigging our results, right? We happen to choose a p-value that's going to cause our results to be significant. In reality, people don't say that. The real reason is there'd be no basis for choosing a really strange number like 0.028. 1%, 5%, 10%. They tend to fit the bill in most applications. Now, here's how we make our decisions. This is important. You want to know this. When the p-value is less than alpha, we reject the null. When the p-value is greater than alpha, we fail to reject the null. We still hold on to it. What happens when it's equal to alpha? It's never equal to alpha. Okay? So you don't have to worry about that. So here's how we think about our decision here. If the p-value is less than alpha, that means there's strong evidence against the null because it's very unlikely I could get the estimator I observed if the null was true. Okay? So we use that other interpretation. It's more unlikely that the population percentage has changed. So we decide there is sufficient evidence. Notice this is like a court trial, the verdict. There's sufficient evidence to conclude something significant happened, that there was actually an effect. We never say the alternative is true, okay? And in fact, a jury never says the person's guilty. They say they find based on the evidence that they're guilty. We never know which hypothesis is true, ever. But there was sufficient evidence to meet the burden of proof. There was enough evidence to make us flip. And we're going to talk about errors in hypothesis testing, okay? But this is important to understand. If the p-value is greater than alpha, we fail to reject, meaning it's unlikely, but not unlikely enough to make us turn over our default beliefs. Notice if you're doing research, okay, the null hypothesis is what everyone believes. If you claim the null hypothesis is not true, if you reject it, okay, everyone has to change their belief. Well, we're not going to do that based on, a little bit of evidence. We need a lot of evidence for everyone to change their belief. So we're going to still hold on to our belief that the value of pi, that should be pi by the way, did not change. The population percentage is still pi naught. Okay. So there's insufficient evidence. So again, we never say the null is true. All we say is we fail to reject, and there's just not enough evidence to actually convince us. So let's put this all together and work on some practice problems. So first of all, if we look at the problem where we had the motorcycle injury rate, we already put in, this should be 425 by the way. I should have changed that, sorry. This is 425. And we're doing what we call a two-tailed test. We're testing to see if it's not equal, okay? That's called a two-tailed test. And we already ran the hypothesis test, okay? We're going to test at alpha 5%. So we go to our output, we look at our p-value. Our p-value is 0.5%. Okay, so alpha here is 5%. Our p-value is 0.5%. So here, 0.5% is less than 5%. We're going to reject the null. Now, how do we say this, okay? So this is a little tricky. So here's how we say this. We reject the null. There was enough evidence to convince us the null wasn't true. So this is kind of like a little template you can use. Like we had a template for describing plots, okay? We start off saying our burden of proof, our standard of proof, which is the significance level, right? That's that dividing line where we go from guilty to not guilty, or fail to reject the null to reject the null, right? So this is our standard of proof. So at a significance level of 5%, we find there is sufficient evidence to conclude that, and then we write the alternative. And what was the alternative? The alternative was that the percentage of motorcyclists injured in accidents after the helmet law was repealed in Florida was not equal to 80%. So we take that alternative hypothesis and we morph it into words. Okay. What about the Colgate? Well, let's run a hypothesis test at alpha equal to 10%. We put all of our input in here, right? Did our calculations. We got a p-value of 0.856. That's a p-value of 86%. Okay. So our alpha here was 10%, but the p-value is larger. It's 86%. So we fail to reject. Now, when you get a p-value for a one-tailed test above 80%, you have to think about why. We're going to talk about this. So how do we say this in words? We failed to reject the null. There was some evidence, but not enough, okay? So we say at a significance level of 10%, same wording as last time, we just changed the value of alpha. We find there is not sufficient evidence to conclude that the percentage of dentists who recommended Colgate brand toothpaste was less than 80%. This is equivalent to a jury saying, at the burden of proof required for a certain type of trial, we find there is not sufficient evidence to conclude this individual is guilty. Guilty is the alternative, what you're trying to prove. In this case, we were trying to prove the percentage was less than 80%. Now, an interesting question is, why was our p-value so high? Okay. When you run a one-tailed test, you're testing to see if it's greater than or less than the parameter value, and you get a p-value greater than 50%, you better check. What happened here? Well, we ran a stupid hypothesis test. We didn't have to run the hypothesis test. We're trying to prove the percentage is less than 80%. And what was our evidence? Our evidence was the opposite. We got a sample percentage greater than 80%. If you went into a court of law, if you were pressing a class action lawsuit against Colgate based on this claim, and the judge asked you, what is your evidence that the percentage of all dentists is less than 80%? And you said, well, Judge, Your Honor, we took a sample and our sample percentage was 86%. What would the judge say to you? He'd say, what in the heck are you smoking? Right? You're trying to prove one thing and your data is showing the opposite. So again, remember, this is important. To run a hypothesis test and for it to be meaningful, the evidence always has to be in favor of the alternative. The alternative is that it's less than. So I should have never run this hypothesis test, but I'm showing this to you as an example of when not to run it. Okay? In order for me to show that it's less than, my sample percentage would have had to have been less than the parameter value, but it wasn't. So this is an example of where you're running a stupid hypothesis test. You can do it, but there's no reason why anyone in their right mind would do it. And if you tried to press an actual lawsuit with this sort of evidence, your case would be, dismissed with prejudice, right? Because you're wasting the court's time. It's stupid, frivolous claim. Okay, let's go ahead and now apply this to the RAD empathy problem. So remember the RAD empathy problem? Go back and review that. What was the sample size? What was the number of successes? What was the parameter value under the null hypothesis? And what sort of test are you doing? Go back and review your notes and find that. And now you'll have a reading quiz question that will ask you those particular details. Okay, now let's take our analysis of this problem a little bit further. Use StatCrunch the way we used it on the past two problems and run the hypothesis test. What is your test statistic? What is your p-value from the output? And what do you decide based on alpha? Our alpha is 1% here. So take some time out and answer those. And finally, we want to state our decision. So the reading quiz is going to give you 4 different choices. And you want to choose the one that would be the correct conclusion based on your answers from the last question. Okay, great video. If you missed those problems, ask me. I'm more than happy to go through them with you because these are important problems and they kind of are baseline knowledge that we assume you have going into the homework. All right, thanks for watching. Again, you have any questions, feel free to ask. This is, along with the sampling distribution, the hardest part of this course. But if you really spend some time and understand those diagrams with a normal distribution and can understand what's going on with the sampling distribution, the rest of the course will instantly make sense. I thank you.